Okay, so first of all, I would like to thank Shiraz for sending me an invitation and allowing me to present my work here. And I was having a stroll in the morning with my mom over the shore, and that really refreshed the memories that we had while working on memory in paradigm. So, so the title of my talk is Holographic RG Flows for Class S Line Defects. And first, I would like to introduce the topic and give a good motivation behind this project. Then I'm going to chalk out the methodology that we used to answer a research question that I was pursuing at UT Austin. And then finally, I will present the flow equations. So first, prologue. So there was a program which was initiated by Chris Beam and collaborators in which they put some theory on a Riemann surface, and then they showed that if you perform a renormalization group on that theory and you go to the infrared regime, then the metric essentially flows into a constantly negative curvature curved metric in the IR. So no matter whatever metric you start with, in the IR you always end up with the hyperbolic metric in the same conformal class.
It's a two-dimensional.
Right, it was a 6-dimensional theory. It was put on R1, 3 times a Riemann surface. And then they performed an RG and then obtained an effective 4-dimensional field theory. It was known as class S theory. And for class S theory, it turns out that the conformal factors are not relevant for the metric. I mean, conformal factors of the metric are not relevant for the RG purposes. That is being expected for class S theories for a long time, but this is what Chris Beam and collaborators, they showed holographically. I mean, it's very interesting paper to read. We can have more discussions. In fact, I will try to explain how they obtained this by this talk.
So just to understand, so you had an N5 plane on R4 times some Riemann surface.
Right.
And you will find the supergravity solution for that. And in the IR, you find a factor of R4 times some other compact manifold, and this other compact manifold is what you're calling this negatively whatever.
Yeah, it's the hyperbolic metric in the same conformal class of the metric that you started off with.
Same conformal class. So just
right.
Y factor flows.
Sorry, what?
Only the Y factor flows.
Right, that's right. Yeah, you can say.
Okay.
So this is what they call as holographic uniformization. Furthermore, they showed that if you introduce any arbitrary or generic perturbations about the metric, then all those perturbations.
Hyperbolic means constant negative curvature.
Right, that's right. It's for the ADS2 kind of metric. So furthermore, they show that if you perform or introduce any generic perturbations about the metric, then all those perturbations are just washed away as you are flowing into the IR. So that means that it's an infrared stable fixed point. So no matter in which direction you are trying to go away from that point, the RG will focus all the flows back into that point. So that was their claim, and that this is what they've showed holographically. So now let me introduce some players in this project. So first of all, there is a mysterious 2, 0 superconformal.
Are you going to review that part later on, or
the part by Beam and company?
no, this RG flow, and I mean, for example, do you land at an SCFT? I didn't understand that.
Yeah, in the infrared, there is an effective 4-dimensional field theory.
Yes, that's described.
And it's
holographic.
yeah, as you're performing, yeah, you can see that from gravity side, as you move deeper into the bulk, that essentially corresponds to performing an RG in the CFT side, right? And that was the idea which was propagated by Polchinski and people.
I mean, I know of examples in which you have geometries which look like ADS4, and it looks like ADS2 plus R2 as you go inside.
Yeah, it's something like that. Yeah.
The appearance of another ADS inside, that you can say that there is a.
Yeah, that's right. That's right. So.
There's some picture like that here.
Yeah, that's right. Exactly. There's essentially the same picture. So you kind of see ADS5 inside ADS7, something like that.
You start with ADS7 with a boundary which is flat space times some surface.
And yeah, that's because of M5. And now I come in.
And then as you come in, you see ADS5 times.
So you don't quite start with ADS7, right? It's only local ADS.
Yeah, asymptotically locally it's ADS7. Yeah, because it's an exotic theory. We will be performing twist and.
You put a fibrate on a Riemann surface.
Yeah, that's right, with a twist.
So how the ADS5 comes in appears inside, that was not clear to me, but maybe.
But it doesn't sound unreasonable.
From a field theoretic point of view, it's, you know, you can think of it as a color supply.
Yeah, no, so I meant that what's the geometry of that thing? So there's some geometry which
both
has
interpolling geometry.
which has ADS5 near horizon
Yes.
thing.
ADS5 times this hyperbole.
Right.
Times S something.
Yeah, some squash deformed S4 in a very specific way.
Fiber, right? Fiber on the surface.
Yeah, that's a fibration, non-trivial kind of thing, non-trivial fibration. So yeah, let me introduce some players in this project. First is these mysterious 2,0 superconformal field theories in 6 dimensions, characterized by the Lie algebra an-1. So it's too long to be a name, so let's call it theory X. And this is a mysterious theory because we don't have any Lagrangian formalism for these theories yet, and it's not even known that such a formalism should exist for these kinds of theories. So in that sense, it is mysterious, but at the same time, they are quite interesting because one can perform several compactifications of these theories. So for instance, if you start with this parent theory, which is theory X, you can compactify this on S1 circle and obtain a 5-dimensional super Yang-Mills theory. You can also compactify this on a Riemann surface. So you put a theory on R1, 3 times a Riemann surface, and you compactify that to obtain a theory of class S. Similarly, you can compactify this on S1 times a Riemann surface and obtain this, and you can perform a series of compactifications to obtain the theory of lower dimensions at appropriate level. So you can do all these kinds of gymnastics, compactification gymnastics, starting from that parent theory.
What is class R?
Class R.
With one arrow going down to class R.
Right, it's also some kind of a compactification on some manifold. I think on 3 manifold or something.
So it's a 3-dimensional theory.
Right, I think so, yeah.
It's a class H also. We had.
You had class H.
Yeah, I got it from NCAT lab, so whatever they're showing there.
4 manifold.
So that's the interesting part. I mean, anyone can play in this kind of compactification game. So
S presumably stands for S duality. What does R stand for? R
I think RS. No, just RS. That was the unfortunate letter that.
And what did H stand for?
H. Yeah, we had some. I think heterotic. There was 0, 2 symmetry into it.
okay, cool. So the theory that we are really interested in is class S theory, and as we have discussed so many times before this point, that the idea is to put this theory X on 6-dimensional manifold, which is R1, 3 times a Riemann surface, and then perform some twisting. So what's that twisting? I'm going to explain later. But presumably, you twist the theory, restore some supersymmetries, and then you start performing renormalization group to go into lower energy regime, which is infrared regime, and there you will get an effective 4-dimensional field theory, and that's what we are going to call classes. So what's a topological twist? So the idea is that since you're putting a theory X on a curved manifold, the curvature of Riemann surface is going to break the supersymmetries because it's going to interfere in the Killing-Spinner equation. So what you can do is you can introduce some external gauge field and couple it with the R symmetry current. So this theory X comes with as a 5 worth of R symmetries, and you can couple the external gauge field with the R symmetry current in a very specific way such that it compensates for the spin connection coming from the curvature of Riemann surface. Once you do that, cancellation happens, and you can restore the Killing-Spinner equation and supersymmetry, make the theory supersymmetric again. So that's the idea, that's the geometric idea. Algebraically, what you can do is you can make a choice. You can make a choice of a product of a subgroup from a product group of a structure group on Riemann surface and the R symmetry of the theory X. And that's what we're going to call SO2 prime C. So this group is generated by this particular element over here. So there is an element in the structure group of the Riemann surface and rotations in 1, 2, and 3, 4 plane. So SO5 symmetry can be considered as the isometry of the transverse trivial R5 fiber. and rotations in that can be described in this form. So with the choice of A equals 1 and B equals 0, we will end up with half VPS twists. We'll just call it half VPS twist because it preserves half of the supersymmetries. And the surviving R symmetry of the theory now is SO3R and the anomalous U1R symmetry.
I didn't completely understand, but is this, are you basically choosing a gauge field that cancels the spin connection on the Riemann surface?
Yeah, that's right.
You have multiple ways of doing it. You pick one which preserves half VPS.
Yeah.
So you could embed that into inequivalent
Inequivalent U1s in SO5.
and you choose the one then.
Yeah.
You want. Fine.
The one that has commutant SO3. So you can think of SO5 as SO2
I see.
times SO.
Block, okay.
Yeah.
Yeah.
Otherwise,
Right.
you could have broken that to.
Diagonal.
Right. Another choice is like A equals 1, B equals 1. Then it's called 1/4 VPS twist. So that's the idea of topological twist here that we're talking.
For any value of AB, it would be 1/4.
Yeah, well, it's nice to have some normalized standard. So
No, I'm just making a physical point that any value of A and B, it would be quarter VPS.
okay, fine. Yeah, I never worked with the quarter VPS thing, so I just worked with half VPS. Okay, good. So now, we define line operators or loop operators or line defects, whatever name you want to call them, for class S theory. So first of all, the question is that why do we even care to study something like this line operator? And the answer is that in order to verify several conjectures and dualities occurring in these kinds of theory, we can use line operators as probes. So for instance, we are familiar with the Wilson line existing in the field theory, and if we apply S duality to that, we get some other line operator, which is magnetic line operator, like Tufta. So here it's nice to have a precise definition of what we mean by line operator or a loop operator. So line operator, it's a point in the R3 space extended in the time direction. That's the simplest way to define that. But besides that, it also preserves a set of symmetries. So first of all, because it's a point, it preserves the SO3 worth of symmetries about that point. So there we have the SO3 symmetry. Then it also has to preserve the SU2R symmetry of the original theory, which was there after performing the twist. And then it also preserves the SO2, 1 symmetry. And finally, it preserves some supersymmetric algebra, which is characterized by this algebra over here. And the phase, so the idea is that once you perform the spatial reflections, xi going to minus xi, then you can conjugate those reflections by the U1R group. And while you're doing that, the supercharges pick up some phase. And that phase is characterized by this zeta. And
many things are not understood. Firstly, how much supersymmetry does your IR theory have?
It's n equals 2, so there are 8 supercharges.
N equals 2. It's a superconformal field theory.
That's right.
Now, what is U1R?
It's an anomalous R symmetry that was originated after performing the twist over here.
So there is an SU2 which is part of the superconformal algebra, SU2R symmetry, because it's an N equals 2 superconformal field theory in 4 dimensions.
It's part of the superconformal group. No, I don't think so.
Well, the superconformal group, N equals n superconformal group in 4 dimensions has a SUM R symmetry. So if you have n equals 2, it is an SU2 R symmetry.
Oh, so that's, okay. I didn't know that.
No, that's what's written down, right?
What?
Surviving R symmetry.
What?
There's an extra U1.
There's an extra U1, so this is in addition to that.
No, the R symmetry is always extra U1 except for n equals 4.
Oh,
Then there's
U2, sorry.
Yes.
Yeah. So this U1 is that SU2 times U1. This is that U1.
Right. Yeah, it's anomalous.
It's anomalous. Can't be anomalous if it's
not
conformal.
Okay. I was under the impression maybe I read it wrong or something.
It may have a Toft anomaly, but it can't be an anomalous because it's part of the superconformal.
Okay.
I'm just trying to understand. Is it part of the
Shiraz, I think he's probably meaning there's an R3 kind of an anomaly, right, which is fine, or a global symmetry.
The Toft anomaly.
There's a conformal anomaly.
Yeah.
That's fine.
Can we? Right.
And what about the SU2 part? That is playing a role?
In superconformal algebra or what?
I mean, the full symmetry group is SU2 times U1.
Right. That's the R symmetry group. Yeah.
Yes. So everything interesting for you is going to happen inside this, the U1 part.
Well, that tells how the vibration should be there, and that tells us how to place branes in the setting in the brain.
Okay.
Somehow line operator breaks U1, preserves SU2.
Preserves SU2.
Yeah. But I don't know how to see that.
I don't think line operator breaks the U1, does it?
Is it?
Well, I was doing some calculations and I couldn't see the U and R breaking. So I'll show the matrix and all those solutions. Sorry, what's it?
Preserve the complete R symmetry?
No, the complete R symmetry was SO5, but after the twist,
No. Complete R symmetry of n equals to 3.
Yeah, I think this anomalous R symmetry is still there after introducing the line operator.
Oh, so that SO3R was my SU2. Is that right?
Yeah.
Yeah, that's right. Yeah.
All right. Thank you.
Good.
Can
More.
you go to the next list of symmetries that you have? Yeah, so you just there the preserved symmetries, right?
What's it?
For any psi, what is zeta? What is zeta? Sorry.
Zeta is a phase that we fix. It's a phase picked up by conjugating the spatial reflections. So it's an involution in the algebra which is produced. It's a fixed algebra of that automorphism
So it
essentially.
looks like that U1R is broken, right? Because you have chosen a particular phase.
That's what I would when you pick a something, then it breaks.
Yeah, that's right. Probably. Yeah. Okay. I'll ask a question in the end and see if this U1R is broken or not. I might be confused on that part.
Supersymmetry subalgebra that you have written OSP 4
Mhm.
star slash 2.
Right. That's the broken one.
So what is the bosonic subgroups here? OSP. So that means there is an SO4 there, right?
OSP is that same as OS? Is
I
that
thought it's the
SP4?
O in the first guy and SP in the
I
last
see.
guy, right?
That's
So the
funny, right?
SP2 is the SO3, right? That's the SU2.
Mm.
And the O is the SO4, and so that's the conformal guy.
The conform because you're saying
No, confused. What is that conformal? Conformal symmetry would be SO3, roughly. The non-compact form of SO3.
because
It's
one
one D.
plus one.
It's just 1D.
Ah.
So it should be OSP3 slash 2.
I mean, I can give you the reference if you want.
I think it's fine with
It's well written there. Okay.
the transfer state.
No, how can it combine with that? That's a
O4,
great
O4 is SU2 times SU2, and locally it's SO3 times. And if you note the nature, it's SO3 times SO2.
Yeah, but you don't imagine the off diagonal parts. Oh,
It's the 4 star.
I see. That seems a bit odd, but
And this is the way they are defining this line defect.
no,
I'm not sure if you
it's
can
not definition,
deduce that.
It's physical, right? Matter of understanding.
That it must preserve certain amount of supersymmetry.
Yeah, I'm not able to
It's an
understand
effect.
this OSP thing that you have written.
Abhijit is asking this. If you've got a one-dimensional line defect, then there's a one-dimensional conformal algebra somewhere.
Right.
Where does that sit inside your OSP forms?
Oh. Okay. Yeah, I don't know about that part. I was just working with this holographically, so I'm not. I don't clearly understand what's happening in the field theory.
But SO2, 1 is the conformal.
Yes.
SO3 is the transverse protection.
Yeah, symmetry wise what you are saying makes sense, but I mean that there is an SO2 there, SO3 there, there is an SO3 outside, that makes it SO4, and then there is the SO2 there.
But
But,
SU2R,
Yeah, the SU2
One
the
is
SU2 there, yeah. But somehow combining the transverse and the seems a bit odd to me. But
I can give you a reference later probably. So anyways, this is a list of symmetries that we are going to preserve.
So, sorry, just zeta, can you say more about what is the zeta, what is the 4 star? I'm not understanding this notation actually. Zeta, you would say what, how the zeta enters into the algebra and so on?
Right, as far as I understand, it's like these supercharges, they pick up a phase once you conjugate the spatial reflections by the U1R rotations. So the phase picked up by supercharges is defined by zeta, and there is an entire algebra in which this zeta appears due to this conjugation. This, as far as I could understand.
I guess another way to say it is that this preserves half of the supersymmetries, right? The zeta is a choice of which half of the supersymmetries.
Yeah, you can say that. Yeah, it's a.
It labels the embedding of the OSP that is written inside the 4D superconforming group. It must be that.
Okay. So it doesn't appear in the 2D superconformal algebra, is that
Right. Yeah.
correct? So it's really a question of how it is embedded into the 4D superconformal algebra.
That okay.
But did you say 2D? Did you just say 2D?
Yeah. So does it appear in the 2D superconformal algebra?
So where is
In the
it?
linear.
1D.
1D you mean 1D?
1D, yeah, 1D, sorry.
Yes.
Yeah, 1D. So it's 1D, yes.
I think the zeta appears in the odd generators of this subalgebra. The way the odd generators of this preserved subalgebra embed inside the original supersymmetry algebra.
Okay.
I mean,
So this algebra will be, will you be talking about it more later or?
no, actually, I was working with the holographic picture, so all I'm concerned is with the renormalization and things like that, not exactly how algebra is embedded. It's a good thing, but I didn't work on that.
Okay, so how does zeta enter into the holographic description? Maybe.
Yeah, that's what I'm going to explain. Yeah, it's the way the M2 brane is embedded in 11-dimensional supergravity solution. I'll make that clear. Okay, good. So, so that's the list of symmetries that we must keep in mind while working holographically with these loop operators. So people have been studying these loop operators, and they classified these loop operators, and one classification, a beautiful classification, was done in this paper written by Drucker, Morrison, and Okuda, in which they classified these loop operators based on the homotopy classes of non-self-intersecting loops on a Riemann surface, on the relevant Riemann surface. So for instance, if you consider this SE2 gauge theory, it's a quiver diagram, then just visually speaking, you can flatten this quiver into a Riemann surface with 4 punctures. So it has got 4 fundamentals over here. That corresponds to the 4 punctures over here. And then this vertical line, gamma, corresponds to a Wilson line. And this delta corresponds to a tooth line. So topologically speaking, they classified all the line operators occurring in class S theory based on their electric and magnetic charges, the way the curve is being wound over this Riemann surface. So there is an entire description of generating electromagnetic line operators based on the winding prescription described in here. It's based on Dan-Truston classification theorems and all those, on all that.
Just say the final result again, please.
That the line operators are classified as per
Line
the
operators of the 4D theory.
are classified by the homotopy classes of the non-self-intersecting loops on a Riemann surface. It's the homotopy class.
That was corresponding to the particular class.
Relevant to that, yeah. So now if you endow this Riemann surface with a hyperbolic metric, that's a constantly negative curvature metric.
And should I roughly think of it as being that the line operators of the 4D theory come from some 2-dimensional operators of the 6D theory?
That's right, yeah.
And these 2-dimensional operators are really,
Perfect.
really wrapping this up.
Perfect, yeah. So that's a surface defect from the 6-dimensional perspective.
Right, where M2 branes go in.
That's right, intersecting branes, yeah. So that's what I'm going to come next. But one more crucial point was that once you endow this Riemann surface with a hyperbolic metric, then each homotopy class has a unique geodesic representative. So we can say that Wilson and 't Hooft operators are classified by the geodesics homotopy classes of classified by the geodesics in a homotopy class on a Riemann surface.
It's clear that they don't intersect the geodesics.
Yeah, they must be non-self-intersecting. At least for A1 theories, I can be sure, but I'm not sure for higher rank theories. If this not
This is just a geometry question. If you have a uniformly curved Riemann surface, you pick a geodesic. Is it always true that it never intersects itself?
oh, I think it might. It's based on the way you are compactifying this Riemann surface, right? I mean, you are imposing a question by a Fuchsian subgroup, and geodesics might intersect. Yeah, I think so. It might. And it does, in fact, yeah. If I remember one of the special case. Okay, good. So.
What is the data that goes into classifying the line operator?
The electric and magnetic charges. So you can literally read off the electric and magnetic charges by the way these windings are there on the Riemann surface. Right, so it's a very interesting paper from the topological perspective. So
Electric magnetic charges make sense when you have U1 theory, right? It would just be numbers, but in general it would, at least for line operator.
Yeah, it's a set of numbers.
It's a representation.
Yeah, in the fundamental represent. Yeah, that's right. It's in the fundamental representation.
So there should be some way of getting that representation label also.
Like what label?
So let's take this surface there.
Mhm.
So that in the case of two M2 branes, that surface would give you SU2 with
Right.
4 flavors.
Right.
And now we consider line operator in the theory, which is of representation J. Okay?
Right. Yeah.
Because it's
Yeah. There's a way. It's written in this paper.
so it just go around J times.
No, it's not. It's not that. Yeah. Yeah, it's clearly written in this paper. I mean, I can refer you to that.
Maybe think in terms of generators of the ring also.
Generators of the ring. Well, yeah. To be honest, I didn't think that much about these things. It's more from a mathematical side rather than physics side thing. At least for me. So right. So that's good. Now, because we are trying to compactify a 6-dimensional parent theory with a twist on a curved background, therefore we must also try to understand the origin of this loop operator from a 6-dimensional perspective, in which, should I just mention, it comes from a surface defect. So one dimension of the surface defect is along the R1 direction, the time direction of R1, 3, and other manifold is along the curve which is being wound over this Riemann surface over here. So that's a 2-dimensional support that supports the surface defect, and it's nicely prescribed in the paper written by Gayato, More, and Knightsky. So now we are in the stage is set, and we are in a position to state our research question, which is that how this loop on the Riemann surface evolves as you are performing an RG. Well, that's the question, and the idea is that this classification was done mathematically for A1 theories. For higher rank theories, it's conjectured, it's hoped, but still it's not proven that this classification holds for all ranks. So that's one thing that we can test using holography, because in holography, and we work in the large n limit. So we are working with higher rank gauge theories.
The loop in the UV is chosen to be on a geodesic or arbitrary?
Yeah, it's an arbitrary loop. Yeah. So that's the thing. So the idea is that as the program initiated by Chris Beam and collaborators, they started with an arbitrary metric, and then they showed that it flows into a constantly negative curvature metric in the same conformal class. Here we are going to show that if you are starting with any generic loop in UV, then you are going to flow into a geodesic in the IR. So that's the complete question that we pursued at UT Austin.
So two things are happening there. The metric is changing, becoming this thing.
Good.
And also the line.
Right. Yes, that's right. But we are going to work with a solution of a trivial flow. So if you start with a constantly negative curvature metric in the UV, it's going to remain same, right?
Oh, so that's your setting.
Yeah, that's right. So that's a
metric to change.
yeah. So the important thing is to see how line is changing. Once you are comfortable with that, you can extend that equation to the changing background. So initially we thought about that using that, but the simplest thing is to start from one step at a time. So
So that would be a purely 4D question, I guess.
that would be purely 4D question.
Because your metric is already this thing. You have already flowed, right?
Yeah, that's right. But you can also do a 60 thing, right? I mean, what's wrong with that?
Yeah, you could, but I mean, if you're holographically uniformized already, then you have flowed here, right? So you just find
So the surface will flow.
surface with
The surface will take some shape in the radial direction.
the line operator surface.
So it's on M2 brane. It will go as you go lower down to some asymptotic form.
Right, good. Thanks. So that's a research question, apparently. So now it's always useful to see the SCFT picture from brane from M theory perspective. So so let's do a revision, and for some people it might be new information. And it said that theory X lives on the world volume of the stack of n M5 branes, and the idea is that rest of the 11 dimensions, which is just the 5 dimensions here, it's R5 fiber, which is trivially fibered over this stack of n M5 brane. It corresponds to the SO5R symmetry. But what we are really interested in is the twisted version of this theory. That means this theory the world volume of the M5 branes must be R1, 3 times our Riemann surface. So so we are interested in twisting the theory, and that corresponds to some non-trivial fibration of this R5 fiber. So the solution that we are essentially interested in, the supergravity solution that we are interested in, is R1, 3 times R3 times Calabi-Yau twofold, and the M5 branes are warping R1, 3 and some non-trivial supersymmetric cycles in Calabi-Yau twofold. R3 here corresponds to the SU2R symmetry, which was unbroken during the twisting procedure. So there are several ways to see how this Calabi-Yau twofold there are several ways to see this Calabi-Yau twofold, and one way is to see that is the fact that this Calabi-Yau twofold is a holomorphic cotangent bundle over a Riemann surface. And another statement is that C is a holomorphic curve in this Calabi-Yau twofold, and this is a holomorphic line bundle over this Riemann surface. Essentially, all these geometrical things come from the fact that some holomorphic two form must vanish in order for supersymmetry to be preserved. So
This is M3 background. This is number 1.
this thing,
Yeah.
this is supergravity background, 11 dimensional. So 4, 3, and 4. So again, here we are looking at the field theory limit, in which branes are just the pro-branes, and there is essentially no back reaction. So again, this is the statement of the geometry. Now we are interested in introducing loop operators in this M brane setup. So again, as we have had discussions, that it must be coming from the intersection of M2 and M5 branes. So we have stack of M5 branes, and there is a semi-infinite M2 brane which is intersecting this M5 brane in certain submanifold. So obviously one leg is going to be in the time direction, and other leg is going to be on the Calabi-Yau twofold, where we have this holomorphic curve known by the name Riemann surface. So that's going to give us the windings and the idea of electric and magnetic charges. And now there is one leg left, right? So there are two spatial legs of M2 brane and one time temporal thing. So now we come to the phase zeta, which was there. Oops. This zeta over here. So the third leg of the M2 brane is in the fiber, which is fiber over this Riemann surface, with an angle, with some angle which is fixed by zeta, with respect to the tangent to this curve on Riemann surface. So it's that particular angle.
Sorry, I didn't understand this last bit.
Right. So understand that that there is some Riemann surface, and that we have some line, some curve which represents the loop operator, and then there is a trivial fiber over this, and then there is an angle which is made by, so let's say this is a tangent to that, and there's an angle which is made by this, so it's zeta is e raised to power iota phi, where phi is the angle between this fiber and the tangent to that curve. No, this is the fibration that we had in the Riemann surface.
Okay.
So it's in the Calabi R2 fold. So yeah, we are not touching R3 fiber as
The
well.
third direction is doing what?
It's lying in this fiber essentially. This fiber is fibered over this curve, but in a very specific fashion.
Sorry, I didn't quite understand the relation between the Riemann surface and the Calabi R2 fold. So can you say how it's exactly geometry is related?
Right. So Calabi
The relation between the Riemann surface and the Calabi R2 fold. What is it exactly?
sorry. What's that?
What is the relationship?
How is the Calabi R2 fold related to the Riemann surface on which you amplify the
Right. So the Calabi R2 fold can be thought of as a holomorphic cotangent bundle over a Riemann surface.
So what does it mean? How? I don't understand those words. Can you define that?
Right. As I thought that it can be.
With this vibration of the U1 that was rotating one of the R2s on the Riemann surface produces for you a silhouette Calabi R2. That's a locally Calabi R2.
Okay, so I should think of the Calabi R2 as a combined, have the directions of the Riemann surface and
Non-trivial vibration, yeah.
Yes.
Okay. But how do you get two more directions?
Because the R2 is fibered over it.
Okay, you take the full R2.
Yeah.
Okay. And then that is the Calabi R2.
Yeah, because we had R5 to begin with, then you break it into R2 and R3. R3 remains as it is, R2 gets fibered
Yes.
because U1 is fibered, right? U1 is rotating the R2.
Okay, fine. Okay, now what is the zeta? How does it work?
Zeta, yeah, I was trying to explain that. It's the way this vibration is done over the loop on the Riemann surface. It makes certain angle with the tangent to that loop, and that angle is phi. So zeta is the exponential I phi thing.
Okay.
I have to say, I haven't understood that either.
What is it that you didn't understand?
I don't understand what this fiber is. I mean, what is this thing?
The M2 brain has two spaces.
So what is the base? What is the fiber?
Base is the Riemann surface, and vibration is the non-trivial vibration that we had in the Calabi R2 fold.
So Naveen is suggesting that this direction is the angle at which the M2 brain meets your Riemann surface. Is this
One of the
This is what I meant to say.
That it would be great if you said it.
Yeah,
It's the word M2 brain. Now, what is
I said the
fiber?
third leg of the M2 brain is along this fiber.
Okay, I understand. Sorry.
Okay. Uh-huh.
You know,
Okay.
just for us, if you stop using words like fiber.
Sorry, I had the pedigree from UT Austin, so I'm well versed with their terminology and things like that.
Fine.
Um,
Now, angle meaning what? This is at the UV?
yes, this is in the UV right now.
So it's the M2 brain hits the UV Riemann surface and then comes out in some direction.
So it's
This
a
is-
yeah,
I still haven't quite understood.
it's a semi-infinite brain. So I didn't understand what you mean by coming out. It's a
So-
semi-infinite brain which is intersecting the M5 brains at its submanifold.
So in the UV locally we've got just an M5 brain. M5 brain geometry. So it's locally ADS7 times
S4.
S4. Now, can I understand this picture in that local? Is this an angle in that local thing?
Yeah, it's essentially a local definition. So once you take the fiber,
Meaning the direction that the M2 brain is That's the world volume of the M2 brain? That fiber?
Yes, that fiber is the world volume of the M2 brain.
Okay, so I take the M2 brain and go on. So this is the angle of what with what?
The angle of the fiber or the third leg of the M2 brain with the tangent of the loop on Riemann surface. So Riemann surface has got its own tangent bundle, right?
Okay.
I mean, it's as you said, it was locally an R2 vibration, right?
Right.
So
You want to pick one direction, you've got two directions.
right, yeah.
Only one direction is left now for the M2 brain to live.
Right. So the M2 brain is a line apart from this.
R2.
This.
R2 space in which it is living.
Yes.
R2 space which is vibration. The M2 brain is picking one particular direction.
Yes. And with this angle,
That is telling you what is the direction it's picking.
I see. So the line on the Riemann surface was part of your R2?
Yeah, well, it's cotangent bundle. That R2 is a cotangent bundle and this is tangent. So there is some, I don't know, there is some will go between the two.
I see. I thought the R2 was totally separate from, because this was the Riemann surface and the R2 I thought was in the.
Maybe you can just draw a local
Well,
coordinate picture.
Modular
Near
tangent,
the-
cotangent.
near a
It's the
point.
tangent.
I mean, what you
Tangent bundle. The R2.
Yeah,
was
let them
the
discuss.
tangent bundle of the Riemann surface.
Cotangent, but
I mean, it's a Calabi-Yau twofold, right?
In the S5, in the S4.
no, but R2 is correlated with Riemann surface.
Look, I'm not
I see.
working with the ADS dual right now. I'm just working in the field theory limit. So there is no S4 and ADS right now. It's just I'm working with this kind of geometry over here. If that makes things
But
clear.
in the ADS it would go in radial direction?
Yeah, in ADS where it will go, I'll come to that.
Okay.
let's just count from the beginning. M2 brain has a time direction with the line defect.
Yes.
R1, 3. Then we have two more spatial directions remaining.
Yes.
One of those wraps this loop on the Riemann surface.
Yes.
The other one takes is another line.
Yes.
The R2 that sits on top of the Riemann surface. That line we have to choose in R2.
Wait. R2 sits on top. This sits on top of the Riemann surface
Well,
means what?
Okay.
It's part of
take
the
a point on the Riemann surface and look at all tangent directions. That's an R2.
Yes. That's.
So among that there is a tangent vector to the curve.
Yes.
You take the tangent vector to the
Yes.
curve. With reference to that, rotate that vector by angle theta in this R2.
In the tangent space of the Riemann surface.
Yeah.
I think this would be coming out somehow.
It's coming out of the Riemann surface. The
Coming
tangent
out
space
is-
is just tangential.
Yes.
In SCFT that would be some radial direction.
Radial direction.
Part
So
of it.
so is this radial direction going the R direction also something to do with the sphere?
Something to do with sphere also.
And it's how much to do with the sphere is this angle?
I think so.
I never thought of that.
Or maybe it's which point on the sphere? Which point? There's some special R2 on the sphere, right? There's special two plane correlated with because of the twisting.
It will not, will it be two plane?
Because
Because it will be a circle, right?
Correct. Think of the S4 as embedded in S5. Then in this embedding S5 there's a special two plane.
That's fine.
Think of S4 just mathematically as embedded in R5. Sorry, R5.
Okay.
Yes. Okay. Now in this R5 there's some two plane, and I was wondering whether this was something about which this thing is at a point on the S5, right? On the S4. This business presumably, at least when it starts off, is a point on the S4 and going out in the radial direction. And I was wondering whether this zeta was characterizing the location of that point on the S4 with respect to this cutting.
Or maybe even how that point moves as you go in radial direction.
Maybe how that point moves as you go in radial direction, though I would
But it's a, sorry,
DQV doesn't move because that's how two brains behave. They sit at a point.
But yeah, the fact that it's also fiber should somehow be.
Yeah, I was thinking that maybe the zeta is just a question about the orientation of this fiber, the gauge field on the S5 and the point at which the two brains were sitting.
Maybe you're saying point on S4 as a function of Riemann surface? No.
I was saying just point on S4 But now point on S4, if you don't have anything else on the S4, is meaningless. But now we've got this plane, right? Or the circle, as you said. This great circle. So now different points are different. There's a point that lives on the circle, there's a point that's completely north pole to it.
No. Because the M2 brane is still on that great circle. Because it's living in the cotangent bundle, right? This leg is going into that R2, the special R2. So it's not coming out of that. It's still in R2. But I think it has to do this angle now in this geometric point of view. What is this? It is indeed this picking a point on this S1, even the great circle. But I think it is telling you how that point moves as you move along the geodesic.
Maybe.
That's the angle.
Okay, I'm sorry I didn't know all this stuff, so bear with me. So, any more questions?
So yeah, so this ADS, you see how the zeta enters the equations. So already we solving some equations in the ADS side.
Yeah, that's right. So we'll be using kappa symmetry constraint and killing spinor equation. So.
So can you say? I guess we can complete it, but can you say when you're wondering of how zeta would enter eventually into the ADS equations?
Yes, zeta enters due to the ambiguity in the phase. So I'll show that exactly. Phase of so when you have kappa symmetry equation, it comes from the kappa symmetry equation. So there is some ambiguity with respect to the phase there. So I thought that phase corresponds to zeta, but I might be wrong.
Phase of which field? Phase of which field?
Phase of some Grassmann number. So I'll show that. So you have this linear combination of supercharges with the coefficients as Grassmann numbers, and once you apply this kappa symmetry constraint, you get some simple equation which has some ambiguity, and that's what I am calling phase. Yeah, I'll try to show and make this point precise.
So this setup that you have in the UV is that you have some wiggling line defect, not necessarily geodesic,
right?
And then the third direction is always in this theta direction. So
right.
That's some supersymmetric constraint. The zeta direction, sorry, the zeta direction. Right?
Yeah, that's right. So zeta appears in that algebra that we were discussing earlier, right? So that characterizes that super algebra.
That's some supersymmetric constraint.
Yeah, I think so. Yeah, it appears in the supersymmetric algebra.
Wiggling thing. So doesn't it already break some supersymmetry?
I mean, remember the definition that I gave was locally, so a local definition. So it might be having something like this. So each point is going to have different tangents, right? But the idea is that the fiber is fiber such that the angle is always fixed.
Okay, so you're saying you have how biggest line defect even if it is not a geodesic on the surface.
In the UV, yeah. That's right. Yeah. Yeah, that's right. Yeah.
But does that then mean? So let's say you start with this geodesic. Okay, now wiggle this in the Riemann surface. What happens in 4D? Because it has to preserve the supersymmetry, so it has to be very rigid. So something has to change then.
I don't think that gets affected because the definition that I took was from this paper in which they precisely define a line defect, a surface defect in a 6-dimensional theory. And in that they make no mention of geodesics at all.
No, but in your this thing, what you will be showing presumably is that this generic configuration tightens to a geodesic, right?
Yeah.
But let's say now you go to that. That's the physical thing, right?
Okay.
And now you wiggle this a little bit.
You wiggle just the loop
then
on the
nothing happens. Nothing happens. Yes.
Yeah, nothing happens. I mean, it's just the angle between the tangent and the fiber. That's what really matters. It's a local definition. It doesn't matter how much wiggling you can tolerate or generate.
So why is it expected you want to go to a geodesic?
Because in the class S theory, the line defects are classified by non-self-intersecting geodesics on a Riemann surface.
No, I thought non-intersecting, not necessarily. You may not say geodesic. You may just say non-intersecting loops.
Yeah, that's what I said. If you endow the Riemann surface with a constantly negative curved metric, then you can replace the statements with geodesics instead of homotopy classes. And because each homotopy class has a unique geodesic representative.
Yeah, but it's not necessary. I mean, maybe it happens but why does it happen that it goes to that particular?
Well, that's the physics part, I think.
But then that
It has to go to a
that is something should change.
If you are wiggling, something should change. You are in the infrared regime of this class S theory right now. So wiggling doesn't really matter. Just like any arbitrary perturbations to the metric didn't matter in the Chris Beam's program, similarly here, any generic should not matter.
But
I mean, from the
if you are saying the full superconformal symmetry is preserved as you wiggle, then doesn't that mean that there is a whole conformal manifold of line operators?
My statement was only concerned with the IR regime in the infrared.
Yeah, so let's say you go to this IR regime and then you have the geodesic.
And now you are wiggling the
Now
geodesic
you
in the
change it a
infrared.
little bit.
In the infrared, right? It doesn't matter. It won't matter at all.
So,
That's the. If it's in the same homotopy class, it won't matter. And that's
so
what
it will
I
stay
know.
that way? It will stay that way?
It will stay what way?
If you wiggle it and you flow down further, would it just stay like that?
Flow down. I mean, you are in infrared. How much down
Yeah,
you want to
exactly.
flow?
So you are saying there is nothing to flow. That's already a.
Yeah.
that's
After
already
geodesic,
a-
the flow is finished.
No. So I don't want the geodesic. I want to move this geodesic a little bit.
Uh-huh.
After that, does the geometry flow further, making it into a geodesic?
After the. Yeah, you can think about this holographically. When you're saying so infrared regime corresponds to the deepest point in the bulk. So what are you doing holographically? Are you coming out radially?
And maybe I think maybe this thing doesn't preserve the superconformal, but probably just the supersymmetry. How big is supersymmetry?
I think it was characterizing the OSP algebra, right? So OSP has a conformal symmetry group.
Yeah, then I'm confused. Because then it will not flow further.
Then it won't.
Flow further. Any configuration would be a stable configuration.
Like if the claim is that the RG flow corresponds to the tightening of the geodesic, and like Abhijit says, if you loosen
Seems
it,
contradictory.
then
If you what?
if like Abhijit said, the RG flow corresponds to the tightening along the geodesics,
Right.
and then I take that geodesic and I shake it a little bit,
Uh-huh.
that should have some physical interpretation because the tightening.
Yeah, that corresponds
crosses
to.
by
Yeah, that corresponds to some non-marginal operators or something like that.
Yes, exactly. It should be some irrelevant operator. So in particular,
Yeah.
a wiggled configuration should not correspond to a conformal. Should not preserve the full OSP this thing, but only supersymmetries. Yes.
Okay. Yeah. Okay, that's the point. Okay, I think I got confused myself.
When you perturb the irrelevant operator, you would break the conformal symmetry. Right? You will just preserve the supersymmetry.
Yeah, that's right. Okay, fine. Yeah.
So still there is a point in picking that particular configuration because it preserves supersymmetry, I think.
Okay, yeah, I didn't think too much about that either. Could be. Yeah.
Does that sound reasonable to you, Siddharth? Sounds right.
Sorry,
am I out of time?
Sorry, just one. I just want to make sure once more what this operator is, just in terms of field theory.
Mhm.
So field theory is M2 brain on Riemann surface times R4. M5 brain,
yeah.
sorry, on Riemann surface times R4.
Right.
Okay. Now, if I there are two things I have to do to specify this operator, presumably. First, just to specify a two-dimensional surface on Riemann surface times R4.
Right.
And second, to specify some data relating to the tensor fields, the analog of the scalar fields.
Okay.
Okay.
Yeah.
Does this angle have to do with the first part or the second part?
Yeah, I don't think it appears in the tensor fields anywhere. So.
Like if you look at Wilson line and n equals 4 angles, if you want it to be supersymmetric, it's A dot dl plus
Some
scalar
phi.
field in some
Right.
this direction. Okay. So all in the first geometrical part, just specifying a two-dimensional manifold, there's some line on the Riemann surface,
Yeah.
and then there's some curve in R4, right?
Right.
And I thought the Riemann surface and R4 were just orthogonal to each other. So there's no sense in which you have an angle between them.
Right.
So I don't understand what the zeta can be in that point.
No, it's not in the R4. It's in the R2. It's a separate space.
Yeah, it is this.
It is this tensor direction. So
Okay.
in the field theory, there's no additional R2, right?
Right.
So
Yeah.
on surface, there's R4.
Right. Yeah.
So it's something to do with which tensors you're coupling with.
Yeah,
Okay.
From an equal to point of view, it's
Okay.
Coulomb branch.
Right.
Because it breaks the U1, right?
Right. So it's some direction relative to a specified distinguished direction, something like that. Okay, thank you.
Okay. Yeah, you can put it that way. Cool. More questions? I'm sorry. Can I still present? I mean.
Please go on, please.
Okay. Cool. Thanks. So that's a field theory perspective. Now in the original paper, Maldacena also found the dual solution of this 2-dimensional, 2,06 dimensional superconformal field theory, which was that it was a dual to an M theory on ADS 7 times S4. But we are interested in some exotic version of this theory X, which is the twisted version. So for twisted version, the statement translates to the fact that asymptotically locally, the gravity background must be ADS 7 times S4. And for a fixed radial coordinate, the topology must be R1, 3 times a Riemann surface with S4 fibration. So, and again, this was the idea that was I was discussing earlier, that Joe Polchinski. What's that?
Topology of the boundary.
No, topology of the bulk for a fixed radial.
R, whatever R means.
Right, in a Poincare chart. Yeah, whatever R means. Whatever R means. Right, so that was the idea that was propagated by Joe Polchinski and several people working on this field, that the radial coordinate is the measure of the energy scale of the conformal field theory. So there are several research papers which are based on this single statement, for instance, C theorem and Z theorems and things like that. So those are quite interesting from the information perspective, quantum information perspective. Anyways, so Maldacena and Nunes constructed the gravity dual of this class S theory, and it was given by this particular 11-dimensional supergravity solution. So the idea is to consider a 7-dimensional gauge supergravity theory and then prepare an ansatz which is in accordance with the twists that were performed in the field theory side. And then finally one writes some BPS constraints to find the solution and then uplift that solution to 11-dimensional supergravity to get this particular solution. So here we see that this ADS5, which is dual to that 4-dimensional theory, we have S2 sphere. Here we have the hyperbolic space, the upper hyperbolic space. So if we impose the relevant question by a function group, then we can obtain a compact Riemann surface here. And then this is one non-trivial fibration over the Riemann surface, and this is one trivial circle. So we see that S4 here has been squashed and deformed as to match the topological twists that were performed in the field theory side.
So you're saying that the Riemann surface curly C, which you have written earlier, is in that?
Yeah, if you impose a question by a function subgroup. Yeah.
Then what we are left with is an R5, of which 2 directions are in the cotangent space to a Riemann surface, and a separate R3, right?
No. We are seeing this from the gravity side now. So,
Right, so the radial direction in the R5 goes into that
okay.
ADS5.
Yeah, sorry, I'm not really sure how dimensions fold in a holographic setup, but maybe you're right. That might be happening, but I'm not sure about that.
No, but from that Riemann surface it should be S4.
Yeah, so S4 can be considered as the boundary of R5. So you had R5, now S4 corresponds to the SO5 R symmetry group, the isometry thing. So this is from the dual gravity side.
You can see that phi is pi bar, right? The page connection.
Yeah.
Sorry, here, what are the coordinates of the Riemann surface? Among these coordinates that I'm trying to understand.
Where is the Riemann surface? Which are the Riemann surface coordinates?
Right, so this is the upper half hyperbolic plane, and if you impose a question by a Fuchsian subgroup, then you can obtain a compact Riemann surface from X and Y.
X and Y.
X and Y.
X and Y.
Right, yeah, that's right.
Okay. Okay, so apart from X and Y, there is theta, phi, sin theta, phi 2. These are S4 coordinates.
Precisely.
They use these, the lines deformed a bit.
Right, right. Yeah, deformed and squashed and appropriately squashed.
Yeah, so that you broken the R symmetry, so they are deformed a bit, but they used to be the S4 coordinates. And X and Y are the, okay.
Right, yeah.
Okay.
If you erase dx over dy there in the bracket, it should be around, is it around S4?
Sorry,
Or it's still
what's the question?
If you erase that dx over dy,
D-
dx over y,
Here?
No, d5 plus dx.
in the bracket,
Okay,
because that's the gauge field.
right.
Then is it a round metric that is parameterized by theta, psi 1, psi 2, and phi?
Yeah, that's right. But there won't be any vibration as such. There won't be any vibration,
Yeah.
but still it would be squashed and
Oh, it is squashed?
yeah, you can see, I mean, for theta equals pi by 2, this S2 shrinks to a point, right? But this is independent. I mean, this is a circle, so there's a squashing. Squashing still remains.
So if you remove the 2 also, the p factor 2 in the second line of the metric, would it be S4 then?
Sorry.
Or
If you remove the 2, then and remove the dx by y, then and remove the dx square plus dy square,
Okay. Yeah.
then is that an S4 metric? Yeah, round S4.
Yeah. That's of course a round S4. Yeah, that's right.
okay.
But still, it's kind of like a product of S4. So it's a product of S2 times S1 times S1.
So it's not an S4.
Right. Yeah. Not exactly an S4.
So why did you say remove the 2? I didn't quite understand the 2.
It looks like theta square plus sin square theta.
From some squashing, but I mean, but how do you see the R symmetry there? So 3 R symmetry here.
Right. It comes from here. So we are placing the brain
Two sphere.
from the 2 sphere.
But of sin theta and sin theta, just to make sure.
Yeah, psi 1
The
theta,
two
psi
sphere
2.
which is made by sin theta and sin theta, and there's and that has an SO3 King vector, and that is the R symmetry.
Right. Yeah. Of the for the theory. Yeah.
Okay.
That's right. And anomalous R symmetry corresponds to this trivial fiber over here. So remember there was a U1 R symmetry, which I said was anomalous, but probably not. So it comes from here. And, right. Good. Any more questions?
Is this just the F5 brain solution?
Right. Yeah.
No M2
yeah,
brain.
no M2 brain. Yeah. So that's what we are going to do next. So as we saw from the field theory side that intersecting brains like M2 and M5 brain, they give rise to this loop operator. So the idea again here is same to place the M2 brain in this 11-dimensional supergravity background, which was I should emphasize that it was Chris Beam and collaborators have shown that this is a fixed point. So if you take a trivial solution of the flow, then this matrix doesn't change. It remains invariant. So this is a simplest solution with static background as per RG flow. So now we are going to preserve all the symmetries that we were talking from the field theory perspective. So first, to preserve SO2, 1 symmetry, what we are going to do is we are going to place the time direction of the M2 brane along the time direction of ADS5 and the one spatial direction along the radial direction. So that's the ADS2 subspace, and that's going to preserve the SO2, 1 symmetry. Now to preserve the SO3 symmetry, we arrange the M2 brane such that it's at the point of the S3 in ADS5. So that preserves the SO3 symmetry. And to preserve the SU2R symmetry, we place the brane at theta equals pi by 2, where this sphere shrinks to a point. In that way, displacement doesn't break the SU2R symmetry, which was supposed to be preserved.
And what was the S3?
So ADS5 can be written as in the ADS5, yeah.
Sorry, I was spacing out. Could you just say your placements again, please, if you don't mind?
Right. So one leg is of the M2 brane is along the time direction in the ADS5,
Yes.
and one spatial leg of the M2 brane is along the radial direction.
Yes.
And the third leg is some curve on this Riemann surface. But it's at the point where theta is pi by 2, such that S2 sphere shrinks to a point.
Yeah, it's like origin of R3.
Okay.
Yes.
Okay. Yeah. And yeah, that's it. So this is the placement which preserves the required symmetries.
The point on S3 again is some. So in ADS5 we have exhausted two directions. One is the radial and one is the
Then there's
in the
S3.
remaining three dimensions you have to take a point, and that is some arbitrary.
Yeah, it can be any arbitrary point such that the isometry is SO3.
Are you using global coordinates and ADS5 or Poincare?
Yeah, we are using Poincare for the ADS. I missed the question.
So where is the S3? I mean,
Oh.
R3, right, in Poincare?
In that case, it might be R3, yeah. Yeah, I have not specified the coordinates yet, but topologically speaking, ADS5 can be seen as dr plus r squared times S3 plus some spatial dimension, right?
So you're using global coordinates there. Okay. I mean, okay. So
your line operator is doing something very simple in the R form, basically. It's just sitting
Right, yeah.
fixed spatial position.
Right. The magic entirely lies on the Riemann surface.
Yeah. Okay, and it also preserves the phi translations.
Right, yeah.
So it preserves the full U2.
Right.
Also, you should say something about zeta, right?
Yeah, zeta will come later when I'll impose the kappa symmetry equation.
No, but now that you are specifying the position, it's dependent on zeta.
So this is the equation over here, and zeta comes in the ambiguity here. I, as such, don't do anything with the zeta over here while placing the M2 brane.
So can we say the next?
I mean, because see, yeah, M2 brane it can be fibered, can be opened up along this fiber phi, but I don't think there is any role of zeta to play here in the placement.
You described it like that, right?
Yeah, that was in the field theory side. This is the gravity side.
No, but I think he's saying that it's at a particular value of theta, namely pi by 2, but some particular value of phi as well. Right? So you have to give a curve there, and then specify at what value of phi the work is.
As a function of the curve?
I thought just fixed.
That's a good point, but the answers that we are choosing, the phi depends on the world volume coordinates of M2 brane.
Okay. So that's where the zeta comes in.
Yeah, that's right. So the constraint equation automatically gives zeta essentially.
So it's not yet completely specified here.
So you
Right.
just allow phi
We are using a generic ansatz for now.
function of the, you just allow that.
Yeah, so I'll show that in the next slide. Yeah. So that now comes my next slide. So here is the ansatz, which is compatible with all these symmetry constraints. So the time coordinate of the M2 brane is along the time. So capital corresponds to the coordinates on the 11-dimensional supergravity, and small r in the M2 brane. So this is the time direction, and one leg of the M2 brane is along the radial direction, and here is where we fix the a point. Let's say x1, x2, x3 are 0. On the S2 sphere, since it's also shrinking to a point at x10 equals pi by 2, so we can also set that to 0. And then x7 and x8 are the coordinates on the Riemann surface, so we will parameterize them as a function using p and q. So p here gives us the measure of the radial coordinate, and q here parameterizes how that curve is there on the Riemann surface. So, and x9 is the non-trivial fiber, and again here we demand that there is some functional dependence of p and q. Now when we impose kappa symmetry constraint, it will reveal what kind of embedding exactly there is.
PQ where what, sorry?
What's that?
P and Q where what?
So P and Q are the coordinates on the world volume of the M2 brane. So it has three. So it has two special legs and one time leg.
Field theory. I see. So you are also letting it depend on the
Radial direction.
Radial.
Yes,
Yeah, that's the new thing that we are doing.
but not on the field theory time, right?
Not on the. Yeah, that's right. Of course. Yeah, because field theory time might be corresponding to this. So, yeah. And we have not fixed any gauge as of now. You can fix any gauge. So now comes the kappa symmetry constraint. So again, people in supergravity community have been decently using kappa symmetry to balance the bosonic and fermionic degrees of freedom. So the kappa symmetry constraint is given by equation 6, and here eta corresponds to the covariantly constant spinors or killing spinors in any geometry, and gamma kappa for M2 brane is given by this over here. So here gamma is the antisymmetric product of gamma matrices on 11-dimensional Clifford algebra, and these are the phi binds, which basically translate from a tangent bundle to curved geometry and things like that. And here capital X correspond to the coordinates on the 11-dimensional supergravity solution. Small ijk indices correspond to the indices on M2 brane. And here is the determinant. It's of the pullback matrix of the solution on M2 brane. So we take that determinant, divide by 3 factorial, and we get gamma kappa. So this is as far as defining definitions are concerned. So the 11-dimensional killing spinors are found by this equation. So this is the equation to find covariantly constant spinors. Here this corresponds to the flux. So when I showed the solution, I didn't show the flux, but flux is there. And it was found by Maldacena and Nunes, and so this G corresponds to the flux, and this equation is kind of like a very non-trivial exercise for a grad student. So, but still it's doable. So, so what the idea here is to decompose the Clifford algebra along ADS5, S2, and a 4-dimensional manifold, which is a Riemann surface or a hyperbolic plane. The non-trivial fibration chi and the trivial fiber theta. So we can decompose the Clifford algebra in these 3 dimensions as prescribed here. And if we put this over here, then this equation divides into 3 parts or 3 categories. And we can solve that to find the killing spinors.
Sorry, just one question. The chi is related to phi that you had in the before?
The phi.
What is chi?
Oh, chi is the right. It's the non-trivial fiber. Yeah, that's right. That we had over Riemann surface. It's
So chi is the same as phi. So C is phi, tilde,
right. Right. It's this thing. Yeah. Sorry. I misrepresented the symbols. Sorry about that.
Sorry. Okay. So just one minute. If you can just go back. I just wanted to understand. Just go back to the slide. Understand? Okay. So F2 is sin tilde, phi tilde, C is xy, and you have phi and theta. Okay. Sorry. Yeah, please. Go ahead.
Okay, good. So one can find the solution. So this is the killing spinor on ADS5. This is the killing spinor on S2. And these are the spinors on that 4-dimensional manifold, which satisfy certain projection conditions. So again, these projection conditions come from the killing spinor equation that we had earlier, I mean from here. So that's right. So now, here we can find the explicit form. So here is the Poincaré patch, and we can find the explicit form of the killing spinors, or whatever they are. Here's the explicit form, and the idea is to match the supersymmetry algebra of the bulk and boundary. So in the boundary theory on a CFT, the supercharges are given by the linear combination with the coefficient as Grassmann numbers over here. The same Grassmann numbers are used here to make a linear combination of killing spinors, which basically tell us about the supercharges of a gravitational theory. So the idea is that now we have this linear combination eta here. So so in the equation, the kappa symmetry constraint here, we can write the eta, and we know gamma kappa, and we fill four blackboards, and finally we get a simple equation here. So so in the equation there is some ambiguity, and that ambiguity is e raised to power I phi naught, which I personally think corresponds to the phase zeta somehow. And this equation is only valid if these two equations are satisfied. So these are what we are calling as flow equations now. And this is for the gauge fixing part. So this
what are these Q's and R's?
right, yeah. So right, so these equations are very simple equations, and even a high school student can understand once the meaning of the symbols is clear. So qx here is the directional derivative of the x coordinate on the Riemann surface with respect to q coordinate. So q was parameterizing the curve on a Riemann surface, and similarly qy is the directional derivative of the y coordinate on Riemann surface with respect to q. So remember, while doing the parameterization, we demanded that x7 and x8 and x9 are functions of q. So it's a derivative there. And similarly, we can take the derivative with respect to p. That's going to give us a vector t, and then we can take a cross product. So this is the precise definition of qx, qy, q phi, and tx, ty, t phi. Direction derivative with phi binds because we are working in a curved geometry. And then now we take r vector as t cross q. So now it becomes a simple high school equation, even if we are if we don't know about complex numbers, then we can write them as a set of 3 equations, and then try to. So these are the essential flow equations that we found. And
Are these known? They arrived in some other context before?
no, so the Chris Beam and collaborators, they arrived at equations for the metric degrees of freedom, and they were different from them because they were second order different.
Equations, but
Yeah.
these are tightening equations, right?
Tightening equations. Well, yeah, my advisor called it shortening equation or something. It depends on the name.
Is this to be? So the thing that they were trying to get is the Ricci flow equations on the Riemann surface, but they didn't. They get something.
Yeah, so this is definitely not Ricci flow, and
Yeah, so I'm just asking if
yeah,
was there a canonical expectation for these equations?
no. So these equations are
Is there a
entire.
standard thing that people use.
No,
Geodesic?
not yet.
Geodesic.
Not yet. So this is entirely new equations which are there in the literature now. And now comes your part to prove whether these equations
Radial
work.
flow with length function. Yeah, so that's a candidate. That's a candidate. It sounds like a canonical.
Yes.
Okay, fine. I wasn't aware about that. But the idea is that to check whether these equations actually work or not. So then comes this slide. So it can be seen that geodesic is the trivial.
Just a question. So the way the phi naught occurs in these equations is one in the right hand side of the first equation, where it will be absorbed by a shift in phi. Is that correct?
Yeah, so this is a constant phi, and this is a variable phi. It depends on p and q coordinates essentially that we demand.
Yeah, so I can absorb the phi naught into a shift in phi. So phi naught defines the origin of the phi coordinates.
That's right, yeah. And that I'm guessing corresponds to the phase, zeta phase in the field theory, but I might be wrong.
Okay.
So in the last slide, we can, so I have seen actually this thing that geodesic is the solution there. And if we perform any generic perturbations about this loop operator, then and perform this RG, so with these flow equations, all the perturbations are washed away, and we essentially again end up with geodesic.
So the flow is for in the R. Can I think of it as a shape flowing in R?
Yes, and in the radial coordinate of the ADS.
So the shape on the Riemann surface flowing in the radial coordinate. I can think of it like that.
Right, yeah, you can.
And is it first order? Is it first order.
It's
equation
first
in the
order,
radial
yeah,
direction.
that's right. And it's also reparameterization invariant and all that.
Seems like a gradient.
It might be.
So, so what remains to be seen is, the big question whether any generic loop evolves into a geodesic in IR, and that requires a rigorous mathematical treatment. That
One way you could try to make progress towards such a thing is if you could prove a C theorem, that there's some functional that decreases.
right, in fact,
The natural functional is the length.
yes, that's right. We, in fact, we did discuss
You did
about this. Huh?
Is it the same?
Yeah, it's the same thing. I mean, we discussed, but my advisor said that it needs a paper of its own, so better leave it for future work. So, so these are,
All this is with Andy?
yeah, Andy. So that's it. That's the final punchline of this project. Thank you very much for your patience and invitation.
ICTS, any more questions?
So when you say there are generic perturbations, you did a linearized analysis.
That's right. That's correct.
The linear perturbations you're saying are diagonal, they are irrelevant.
Yeah, they relax
But
and
you want to know
decay.
what happens for beyond that. Is that it?
What?
What?
I'm- Yeah, in fact, there's a caveat there. I mean, so the entire evolution is essentially fixed by the initial data, which is the way the curve is there, and the first time derivative. And depending on the choice of first time derivative, the perturbations either decay down or just blow up. So we thought initially that
Wait,
it
I thought it was a first order equation.
right.
So why isn't it completely fixed just by what the shape is?
It's first order in time and space.
Time, I thought nothing was happening in time.
No, I mean,
No,
no, it's sorry. So we see there are derivatives of q and p here. So p is the radial, corresponds to the radial coordinate essentially. And q was the way it was parameterized. It's a way of parameterizing the shape of the curve.
Right, when you say time, you mean RG time.
RG time, yeah,
Which is the radial coordinate.
the radial coordinate. But I think I didn't make it clear whether.
No, I still haven't understood. I mean, if at any 1 hour I give you the shape, does that completely determine the flow?
No, you have to also specify the first time derivative.
So it's second order in radial derivatives.
Yeah. So first order in space, but I don't see any second order.
The function and its radial derivative.
Yeah, had it been a first order equation, then just the shape would have specified it.
Yeah. Yeah, that was the thing that we were confused. I was confused essentially. But it turns out that so the final equation that we get was a second order differential equation. So
In R.
in R, yeah.
Second order.
Yeah, in R. So if you combine, so there's a way to combine these equations, and when you combine them appropriately, then you get a second order differential equation in R.
Is there a way of looking at it so that it's first order differential? Are you losing information by combining? Or you combine 2 degrees of freedom and combine?
Yeah, so
It's a second order differential
equation in P and Q both. I mean, if you combine these two equations. So the idea is that to perform linearization of these equations and feed in the arbitrary perturbations, and in order to get a degree of so there was a degree of freedom of perturbation along the feed direction, and once you write down the equations, the linearized equations here, here, and here, and try to eliminate the other variables, you get a second order differential equation in perturbation of phi, and that second order differential equation was in P and Q.
Yeah, sometimes you can iterate first order equation twice to get a second order differential equation, which makes it easier to solve, but then you lose that.
Yeah, we couldn't find what information we are losing, but you have any suggestion for knowing that? because
the first question is just in principle, does the shape determine the flow? That's
yeah,
the important question.
that's right. These set of equations are first order in radial.
Roughly, can I think of this as roughly coming from extremizing an area? I know it's not quite that, there's some flux and so on, but suppose for a moment I took a 3-dimensional area or volume and I was extremizing. Then that would give us apparently second order equations. making that apparently second order system a first order system? Or is this what you're getting? I mean, that's basically my question.
Okay, so.
I mean, a non-supersymmetric version of this M2 brane thing would be a second order thing.
Okay.
And then you would need to specify shape at first order. But sometimes supersymmetry helps you to better it.
Yes. Okay. Right, so again, these equations are coming from this kappa symmetry, and that's where the supersymmetry comes into action. And we get these three equations over here, and these three equations by themselves are first order in radial time, RG time. Now when we try to analyze the perturbations, then as you said, we have to reiterate and get the second order differential equations, and those essentially give us the blowing up perturbations and decaying or relaxing perturbations, whatever, depending on the time derivative.
Blowing up perturbations also?
Yeah, so we thought that it belonged to a Coulomb branch or some Higgs branch or something like that. Because in Chris Beam's project also, they also get some blowing up perturbation, and they mentioned that it corresponds to some non-physical thing. So it's there in their paper. So it's in one sense, it's a good thing because we are getting the similar results which we must get. But on the other hand, I personally don't exactly know how to explain that. So
we are seeing some wiggles blow up, some wiggles in the Riemann surface.
Depending on the time derivative, choice of time derivative. I mean, wiggles can be any generic, but the way you said the first time derivative, they are going to either blow up or decay.
There is not if something blows up. First order even. It could be first order. Okay. Any more questions?
Since we are talking about the Zeta, so is the dependence on phi naught essentially trivial in the solutions? That is, I can set phi naught to 0 and get the solution for any phi naught by just phi naught equal to 0 solution?
Yeah, I think so, yeah. Right.
Okay. Yeah, that's all I have.
Right.
Okay.
Loga, before you go, you haven't visited the IFR in a long time. So this time it has to be at least 2 weeks.
Yes.
So next semester, please come. We're gonna call you every week till you fix a date.
Okay.
Okay.
All right. Well, thank you very much for your patience and your decency. Thank you.